In this video, I will review absolute value functions, and I'm going to review them according to this plan that I laid out in one of the previous videos called precalculus review. And the plan is to review the prerequisites first, and then review all these properties and features. Um, and let's start with the prerequisites. First, we'll talk about operations, and um, there aren't too many prerequisites here in terms of arithmetic, but we do have the operation of absolute value after which the functions are named. So you have to be able to work with absolute values, and that means you have to be able to evaluate absolute values, and you have to be able to use the properties of absolute values if necessary. Now, in regards to expressions, you have to be able to kind of pull out that negative sign from the absolute value sometimes. So you should know that absolute value of negative 2x, it will be the same as the absolute value of 2x. There's no need for a negative sign inside of the absolute values. Now, when it comes to equations, for example, when you need to find the x-intercepts of the absolute value function, you may end up with the absolute value equation, which you absolutely need to know how to solve. And how do we solve absolute value equations? We use the property, and we can call it the absolute value property, I guess. That is, if what you have on the right side is positive, then what's inside of the absolute value is either equal to that or the opposite of that. So that is if the right side is positive. If the right side is negative, then you have no solutions. Why? Because absolute value represents distances, and distance cannot be negative. So absolute value equals to something negative has no solutions. On the other hand, if absolute value is equal to 0, that can only be due to what's inside of the absolute value is equal to 0, which then, if you solve it, will give you the solution set. So this is again a brief overview of how to solve absolute value equations. If you need more details, please let me know in the comments. But again, this is what you've studied in algebra. Now I'm just kind of summarizing it for you. Now that we have reviewed the prerequisites, we're moving on to answering all of these questions, and let's start with the form. When it comes to the form, absolute value functions are the such that can be written like this. And if you set h and k equal to 0 and a is equal to 1, you end up with the most basic, the simplest absolute value function, whose graph is shown right over here. Now, to produce this graph, you can throw some points in, but at some point you should just remember that absolute value is the same as the identity function when x is greater than or equal to 0, and absolute value is the opposite of that when x is negative. Now, it's also important to remember that all other graphs can be produced by using linear transformations. However, you will never have to apply a horizontal compression or a horizontal flip because of the property of the absolute value that allows us to, as shown in this example, to factor out anything negative and any positive number out of the absolute value. So you can simplify this absolute value function to look like this, and as you can tell, there is no need to interpret what's inside of the absolute value using linear transformations. You can just do the translations and vertical stretch. All right, as I said, we use linear transformations to graph most of the absolute value functions. And how do we do that? First, we plot the vertex by reading h and k. Then we plot the points closest to the vertex using the that coefficient in front of the absolute value and the sign, so it may open up or down. And then we draw the V shape passing through those points. Now, depending on the combination of values that you get for the leading coefficient, or the sign in front of it, you may end up with two x-intercepts graph that opens up. So it's going to look something like this. One x-intercept that looks something like this, and no x-intercepts that looks something like this. On the other hand, you may end up with two x-intercepts with the graph that opens downwards, one x-intercept, one the graph that barely touches the x-axis, and no x-intercepts if the graph opens down below the x-axis. Now that you have the graph in front of you, you should be able to answer questions about the domain and the range. The domain of an absolute value function is all real numbers without any constraints. And the range of an absolute value depends on, again, the combination of the leading coefficient and the vertex. So if the coefficient is positive, then the range is all the values from the y-coordinate of the vertex going up, and when the coefficient is negative, the range is all the values from negative infinity up to the y-coordinate of the vertex. So you should be able to summarize that off the top of your head. It's very easy to produce, to answer. These questions are very easy to answer. Talking about intercepts, when we're talking about the y-intercept, it's pretty much evaluating the function at 0. When we're talking about x-intercepts, we're going back to solving absolute value equations. So as long as this negative k over a value is positive, then you will have two solutions to these equations, and therefore you'll have two x-intercepts. If this value is equal to 0, this is when you have one x-intercept, or when this equation has one solution. And again, when negative k over a is negative, this is when you have no x-intercepts. And again, based on the combination of those numbers, you should know which of these 6 cases you are dealing with just by trying to find the x-intercepts. Now, you should know that absolute value functions do not have asymptotes. You should know that absolute value functions are continuous on their entire domain from negative infinity to infinity. However, their decreasing behavior changes halfway through. So if you have a V shape that opens up, then to the left side of the x-coordinate of the vertex, the function is decreasing. Again, this is what the V shape looks like. It's decreasing, then it's increasing. If it's upside down V shape, then on the left side it's increasing, on the right side it's decreasing, and you should be able to summarize those properties really quick. Now, V shape is clearly not one-to-one. However, absolute value function can be rewritten as a piecewise function with two linear pieces, each of which is then one-to-one. So for each branch of the absolute value function, you should be able to find the inverse, right? So for the right side, it's going to be this line with the slope 1 over a, and for the left side, it's going to be this line with the slope negative 1 over a, which is the opposite of that one, which kind of make sense. So once again, the absolute value functions are not one-to-one, but each of its branches has an inverse because each of its branches is one-to-one. Now, when it comes to symmetry, absolute value functions do have the axis of symmetry that passes through the vertex, and whose equation, so it's going to be a vertical line, and its equation will be x equals h. I actually have it right over here. And this is what I call axis of symmetry. And when h is equal to 0, then this is when we call the function even, because when h is equal to 0, your graph or your vertex will be on the y-axis, and then it will produce this symmetry, which we call even. Now, some special features of absolute value functions. Well, it's the first time I had to say the words piecewise function, so that makes it somewhat special. But this whole piecewise function interpretation also gives us an additional definition to the absolute value. So instead of thinking of absolute value as the distance to the origin, we actually think of the absolute value this way. It's x when x is not negative, and it's the opposite of x when x is negative. So that makes it somewhat special. And here's an example of writing an absolute value function as a piecewise function. Now, let's talk about finding equation. And when it comes to absolute value equations, so technically we have an absolute value function that looks something like this. So technically we have 3 parameters, so we probably need 3 points, and there is only one absolute value function that passes through any 3 points. I guess, is that true? That's actually an interesting question. So if the points are like this, then definitely there's an absolute value function. But what if this point wasn't there? What if this point was here? Is there a function? I guess it doesn't mean that there is an absolute value. Oh no, yeah, of course there is one, right? So it's just going to be something like this, right? So I think it's true. So given any 3 points, there is only one absolute value function that passes through those 3 points. However, while theoretically this is a easy question, practically we really not that interested in answering this question. So you probably will never see a problem like this. Now, when it comes to applications, you have to again remind yourself that absolute value represents distance, and therefore absolute value functions can represent distances as well. So here's an example of an absolute value function that represents a distance from some unknown number to 3. So that gives it one application. And absolute value functions are great for practicing linear transformations because they are easy to graph, um, and therefore serve very well as a playground for linear transformations, like I said. So this concludes a brief review of absolute value functions. If you need more details on any of the slides, please let me know.